What if weather meant metal rain? Sunsets were jet black, and the seasons roasted an entire hemisphere in hours. Welcome to the galaxy's most horrifying planets, real worlds that make science fiction look gentle. In this video, we'll unpack the nightmares astronomers have actually found. A hot Jupiter where iron vapor condenses into molten rain, a cobalt blue giant that hurls glass sideways in supersonic winds, pitch-black planets that swallow starlight, and a world on a torture orbit that flash fries in a single swing past its star. You'll see how these extremes form, what they teach us about planetary physics, and why they reshape our hunt for life. Imagine standing under a sky so hot that metals evaporate. That's JWST 76b, a hot Jupiter hugging its stars so tightly that one side faces eternal day. On the day side, temperatures soar above 2,000 degrees Celsius, hot enough to vaporize iron. Powerful winds then ferry that metallic vapor to the cooler night side, where it condenses and falls as molten iron rain. It's not just a scary headline. This is chemistry in overdrive, driven by brutal stellar radiation and permanent day-night locking. Now meet HD 189733b, famous for its deep, eerie blue hue. Beautiful until you learn that its color likely comes from silicate particles high in the atmosphere. Translation: conditions can form glass droplets, then sling them sideways in ultra-fast winds measured in thousands of kilometers per hour. Think sandblaster scaled to a planet. These winds are powered by extreme temperature contrasts and a bloated, heated atmosphere that can't settle down. Together, these two worlds reveal how alien atmospheres manufacture weather from rock and metal, not water. They also help scientists stress test models of heat circulation, cloud chemistry, and wind dynamics under star broiler conditions, insights we need to interpret telescopic spectra and spot the rare, calmer worlds where life might stand a chance. Some planets are terrifying because they're nearly invisible. Trace 2b reflects less than 1% of incoming starlight, darker than coal, likely due to light-gobbling molecules and cloud-free, heat-puffed air. Orbiting scorchingly close to its star, it glows in thermal infrared, but to your eyes it would be an obsidian orb, a heat lamp disguised as a shadow. JWST 104b is a sibling in darkness, absorbing roughly 97% of starlight. Worlds like these force a rethink of cloud physics. With intense heating, reflective condensates vanish, leaving atmospheres that drink the light. At the opposite extreme is KLT 9b, among the hottest exoplanets known. It swings so close to a blistering, blue-white star that daytime temperatures exceed many steel melting points. Molecules split apart. The atmosphere becomes a high-temperature chemistry lab where even metals can exist as individual atoms. If Trace 2b is a cosmic blackout curtain, KLT 9b is a welding arc. Why care? Because albedo, reflectivity, and temperature sculpt everything we can observe. How bright a planet looks, which gases survive, and whether clouds can form. Dark and ultra-hot worlds act like boundary markers for atmospheric stability. Understanding them helps us avoid false positives when we analyze milder, potentially habitable atmospheres. If you prefer variety, HD 80606b provides thermal whiplash. Its orbit is wildly eccentric, more comet-like than planetary. Most of the time it cruises far from its star, then, once per 111-day orbit, it dives perilously close. In that brief, brutal encounter, temperatures skyrocket by hundreds of degrees within hours, igniting shockwave storms and supersonic winds as the atmosphere scrambles to redistribute heat. Imagine a planet-wide heat flash that flips climate from bake to broil in a single day. Now shift to a different horror, lava-locked surfaces. 55 Cancri E is a super-Earth so close to its star that a year lasts less than 2 Earth days. Dayside temperatures can melt rock, creating a world that may host magma oceans, vaporized minerals, and a thin, dynamic envelope of rocky gases. Instead of water evaporating and raining back as liquid, you can have rock evaporating and condensing as stone, cycle on repeat. These orbits and proximities aren't curiosities, they're crucibles. They tell us how gravity sculpts climate, how quickly atmospheres respond to violent heating, and how close rocky planets can approach before losing their air entirely. If habitability is a narrow lane, These worlds show us the guardrails and the cliffs beyond them. From iron rain and glass storms to light-eating darkness, stellar blowtorches, and thermal whiplash, the galaxy's worst neighborhoods teach us the physics of extremes. They calibrate our instruments, refine our climate models, and reveal how radiation, chemistry, and gravity conspire to build then break worlds. And that matters, because every extreme we understand makes us better at recognizing the rare, gentle signatures of potentially livable planets. If you love this tour of cosmic nightmares, hit like, share it with a space-curious friend, and subscribe for smarter space stories. Tell me in the comments, which planet wins your Nope award, and what should we investigate next?